summary for those of you just joining us on our journey here. We're trying to read chapter 2 of our book for this week, actually last week as well, and we're talking about the Cauchy integral and some results that relate to it. We'd like to try to prove today that the criterion for existence of the Cauchy integral is continuity of the integrand. And so we'll work our way up to that. We did some preliminary stuff last week. We proved the bosonal wire stress theorem. What's that? Amanda, what's the bosonal wire stress? Oh, God, don't look at me. Just look me in the eye and tell me. Okay. Anybody?
I remember from analysis by Christine.
Okay. A bounded infinite set of real numbers has a limit point. And how did we prove that? Right. He's giving me the, he even did the square brackets. Look
This
at that.
is the signal for the nested interval.
Okay. The round brackets, square brackets. He did it. You have what was the theorem that we used that activated our proof for the bosonal wire stress? Nested interval theorem, Cantor's intersection theorem, which in the context of real numbers is the nested interval theorem. So how did we prove that? We looked at the soup of the left endpoints, in for the right endpoints, watched the norm collapse to nothing, and we proved that there was a point in common for them all, and that was the intersection. There's one unique point common to all the nested intervals. And then we discovered with the bosonal wire stress theorem, this is mostly for Dave's benefit, or Doug's too, I guess. Doug missed this. We took an interval, bounded infinite set of real numbers. So here's the real number line, here's 0, and this set of real numbers is distributed out here. It can be quite a pathological set, we don't really care. We capture it in a closed interval. Since it's bounded, we can do that. We split that interval in half. One side or the other has to be infinite. They both can't be finite, or it wouldn't be an infinite set, right? S would not be the infinite set. This is supposed to be a representation of S, the arbitrary set of real numbers. So we cut this baby in half, and we go with the infinite semi-interval. We repeat this construction. Split him in half. One of these two halves has to be infinite. Split him in half. The one that is, one of those has, and what do we get? A nested sequence of closed intervals whose norm approaches 0. And what does the intersection theorem say about that? There is some point somewhere that's in them all. That point may or may not be in the set S, but what is sure is that that's a limit point of the set S. Because in any neighborhood of this point, little open set, blowing this up, here's that point we have found. Remember, there was a sequence of intervals that this is how we got lambda, right? These things collapse down to this one point. So if you pick an epsilon, let's say epsilon, this is lambda minus epsilon, this is lambda plus epsilon, so we have a little open set containing lambda. One of our infinite intervals, right? There are an infinite number of points of S within epsilon of lambda. What's that mean? It means by definition that that point lambda is a limit point of the set S. And that's all that the bosonal wire stress theorem claims, that this thing exists. The limit point exists, and you have a bounded infinite set. Why are both of those conditions necessary? What if it's unbounded? You can have an unbounded infinite set with no limit points. What would be an example of one? Here's an unbounded infinite set. Are there no limit points for that baby? Are there? No. What if it's a non-infinite set? How could you have a limit point in a non-infinite set? Could you do that? No. Here's why. This might be helpful. Suppose we claim that there's a set S, and S is finite. Those are points of S. And let's just say, okay, we have a limit point here. All right? I measure the distance from lambda to each one of these finite points. And I choose an epsilon equal to 1/2 of the min of lambda minus s sub k over k is a finite set, right? There's only k, these things. All right, so here I am. How many values of s are going to be within epsilon of lambda? None. Right? None. So finite sets can't have limit points. Unbounded sets, they can have limit points. Give me an unbounded set that's got a limit point.
1 over n.
That's bounded. It's contained in the closed interval 0, 1. Just put some other extra stuff on it. How about 1 over n for n, right? So what that is, Dave, is this is your intuition. It's 1 over 1, 1/2, 1/3, blah, 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 that way, and 2, 3, 4, 5, 6.
Oh, okay.
You know,
Okay.
there's the limit point, and it's unbounded. So you can certainly have an unbounded, you know, either one of the other things. Okay. Oh, that's a 4.
Yeah, I know.
Yeah.
It's supposed to be the same.
Yeah.
Yeah.
Okay. Bolzano-Weierstrass. Bounded infinite set of real numbers must have a limit point. So if the set S is closed and it's bounded and infinite, what can one say about S having the limit point within it itself? The limit point would be inside it, right? Could we then construct a sequence converging? Here I claim the following. A bounded infinite closed set of real numbers contains a sequence, a convergent sequence. What I'm really doing here, and this was the sequential compactness idea. Okay. So I have a bounded infinite set of real numbers. Limit point exists by Bolzano-Weierstrass, and closure means that lambda is in the set S, right? S is spread out all around back here. So lambda is in S. All right, now let epsilon sub n be 1 over n. So epsilon 1 is 1, epsilon 2 is 1/2. Since lambda is a limit point, I can find an x1 that sits inside the interval lambda minus 1, lambda plus 1. And then I can find an x2 inside that. And these need not be the same, right? Because I have infinitely many points arbitrarily close to lambda, I can make sure that these two things are not the same. And I can continue with this construction indefinitely. I claim its sequence xn converges to lambda. Right? You give me a tolerance, epsilon. I will go find one of my subscripted epsilons that's less than that. And then once I'm past that index, all the other epsilons are smaller, and I'm closer. I have all my subscripted x's are within that tolerance of lambda, right? So I have engineered a sequence that converges to the limit point. What's the definition of sequential compactness again, Matt? A set is sequentially compact if every sequence in the set if every sequence in the set contains a convergent subsequence. So is set of natural numbers sequentially compact? Is the set 1 over n, n and n, sequentially compact? Remember, the limit has to be in the set. The limit here is going to be 0, right? Any sequence in this set has to have terms with 1 over arbitrarily high ends, right? So the only place that this thing can go is to its limit point. Its limit point is 0. 0 is not in that set. So even though this converges, it converges to something outside the set. If we unify that with 0, is that sequentially convergent? Or sequentially compact? Yes, it is. Here's a fact to remember. A sequence and its limit is always a compact set.